We'd like to move on now to talk about how we can use the ideal gas law to determine the number of moles there are in a gas, and then talk about how we can integrate the ideal gas law with some of the properties of chemicals that we already know are unique to specific chemical compounds like the molar mass and the density, and talk about how we can use the ideal gas law to directly calculate a gas's mass, a gas's molar mass, or a gas's density, and thus use the ideal gas law to start opening a window on the stoichiometry of gas phase reactions. So as we move on to section 8.3 in the Openstax textbook, we're going to first talk about how we can integrate the ideal gas law with what we know about density and molar mass to calculate the density or the molar mass of a gas sample directly. And this is a particularly important skill because historically, so much of what we know about the fundamentals of chemistry was determined through studies of gas phase chemical reactions, which were key to the development of the chemical tools and concepts that we now have to use reflexively to solve almost any chemistry problem. Like the determination that molar masses were specific to pure chemical compounds, the concept of reaction stoichiometry, and the law of conservation of matter were all primarily demonstrated first with gas phase reactions. And you'll not only gain a better understanding of historically how experimenters came to determine these concepts and laws, but also you'll be able to recreate some fundamental experiments that would allow you to determine a compound's molar mass with just a good understanding of gas phase chemistry and how properties that we already know are unique to a specific chemical like density or molar mass can be integrated with the ideal gas law and thus used to determine density or molar mass of a compound in the gas phase from measurements of pressure, volume, and mass. So first we want to show you how to integrate the concept of density with the ideal gas law in order to calculate the density of a gas phase sample correctly, directly. Remember that the density of any material is equal to the mass of the material, lowercase m, divided by the volume, capital B. The density of a gas can be obtained directly from the ideal gas law if we know the gas's molar mass, which is typically abbreviated capital M, capital W, but in gas phase chemistry is abbreviated with either a script M or an italicized M. So if density equals mass over volume, we can rearrange that equation to say that volume is equal to mass divided by density. That's just algebraic manipulation to solve for the volume. We can now interface this with the ideal gas law by plugging in m over d for the volume V and rearrange the ideal gas law to say that the density of a gas is equal to the mass of the gas times the pressure divided by the number of moles times the gas constant times the temperature. We can then factor out the mass divided by the number of moles, and remember that mass over number of moles is how we define the molar mass. Fundamentally, that's what the molar mass is, mass per mole. So if we have lowercase m, which is mass, divided by lowercase n, which is moles, and we factor that out of the ideal gas law, we now have the molar mass, which I'll abbreviate with an italicized m. And now the ideal gas law also tells us that the density of any gas sample is equal to the molar mass of the sample times the pressure divided by the gas constant divided by the temperature. Now, the next thing we'd like to do is take a look at how we can use experimental data from a gas phase sample to determine the density of a gas given a known set of pressure and temperature conditions.